Yes. Yes. Sure, sure.哦，没事，我也好了。
The speaker for signing the consent.
Speaker.
Yeah.
Basically. Okay, sure.
The consent form to like after microphone.
Oh, okay. Give me let me click this.
Take it.
The evolving landscape, just. This is the evolving landscapes.
Yes, it is.
We're taking pictures. Can we just put our poster on any of the boards?
Check the board.
Yeah.
Maybe I don't have to be.
Oh, there's a schedule. Yeah. Okay. Thanks for organizing.
I
was joking that this is the fourth session of ISRA.
mean, I know it is. You have cycles in there.
I don't think because I don't work against
I'm glad it was there. I don't think I could have made it when it was Friday, so.
Okay, so initial so we and this and then that's called we can also like finding a place yeah to see
That makes sense. That's
well, government will be eventually Can imagine a process of the same crowd that is going to take attend this workshop today. We all set?
Good.
Okay, shut up.
So welcome everybody, and thanks a lot, Sean and Ravi, for organizing this workshop. You did a superb job in the organization, and it's really an honor to me to be here to give the first presentation. And so let's start without further ado, like Lourdes was saying. Today I wanted to talk to you about technologies we've been researching and developing for application in the ENT field, mostly on the upper air digestive tract. Sorry. So going directly to the topic, the upper air digestive tract cancer is one of the leading cancers affecting persons all over the world, and it's responsible for a lot of deaths, estimated 500,000 per year. And the incidence rate for this kind of cancers have been increasing, and also the mortality rates, which are correlated to population aging and HPV infections. Most of the cancers, the vast majority of the cancers are squamous cell, in this area are squamous cell carcinoma, which meaning they're superficial tumors. And most of them occur on the vocal cavity and in the larynx. So they are treatable with surgery, and if they are detected in early stage, the success rate is very high and the survival rate also high. But there's many challenges. So this is how the cancers are detected. So when you have throat pain or some kind of problems on your mouth or throat, you go to the clinic and see the doctor, and what they typically do is an endoscopic inspection. So they insert this very small flexible endoscope into your nose and use that to look around and try to detect diseases. The challenge here is that the early stage diseases in this area are very difficult to detect. The tissues in this area are very heterogeneous, and that requires a lot of experience from the clinicians to try to understand and recognize malignancies when they are in early stages. The result is that globally on the statistics, only about 50% of the tumors in the upper air digestive tract are recognized at an early stage, early localized stage. There's another challenge involved here is that when there's suspicion of tumor, they're not so sure, or also to confirm, they have to do incisional biopsy, which has their own risks and possible complications associated to that, like discomfort, bleeding, and possibility of infections. So we think that technology can help here, but also on the treatment phase, when patients have tumors and they have to be operated, so they are brought into the operating room, and this is kind of the setup, the standard setup they use for the state-of-the-art procedure for treating disease in this area, which is called transoral laser microsurgery. Basically, the patient is fully anesthetized, put on the operating room, and they operate through the mouth. So they has to be well positioned so you can see through the mouth. Very often is required to use what they call a laryngoscope, which is a metal tube inserted into the mouth of the patient, so that you can get this direct line of sight to the area that you need to operate on. Surgical microscope is needed to get an enlarged field of view of the site, because this is typically very small areas, and they use instruments like you see on the table there, very long forceps that they need to control with one hand, and the other hand they control a joystick that moves a high-power surgical laser beam to do these very precise cuts and ablation procedures. Also here, many challenges. The ergonomics, as you can possibly notice, is not the best. So there's also the instrumentation is very, I would say, rudimentary, very manual instruments. Everything they require micrometer precision on the motions, but everything is very manually controlled. And the result is that up to Also, the margin of the tumors are difficult to identify from this visualization. So the results that up to 20% of the cases, the margin, surgical margins are positive, meaning that they left the tumors in the patient. So 20% of the cases, the patients have to be reoperated, which is kind of a big problem, not just because of the costs, but also because most of these patients are elderly people, already fragile, and operating twice is should be avoided. No? And overall, the long training curve also to use these instruments and become good at this operation. So in this context, we've been doing a lot of research recently, and as roboticists and engineers, we see the potential of robots to help here, and also AI. For the first part, for the diagnosis, detection and diagnosis phase, this is kind of what we envision and we've been working on recently, is the development of AI-powered algorithms that can detect and diagnose the tumors automatically, looking at the same images as the clinicians are looking to do this inspection and detection. And the CASE is the computer-assisted segmentation, so we are also looking into bring this technology to the operating room to help delineate the margin of the tumors, to reduce those 20%, hopefully ensure that the surgeon removes all the tumor from the patient and not leave anything behind. So the idea here is to, again, improve the detection and diagnostic capabilities of the surgeon with an assistive system, reduce the misdetection, so we detect tumors at earlier stages, which leads to better quality of life for the patients, better survival rate and everything else, and enhance the tumor margin identification. And if we know where the tumor is, its size, its margins, we can also use that for computer-guided surgery. So to start on this, as you probably know, for the AI, you need a lot of data to train these algorithms. No? So we started working with the patients and convinced them to help us, and they actually invest quite a lot. They bought into the idea, they really liked it, and they selected and annotated thousands of images for us. In fact, more than 11,000 images that they went through their databases, collecting new videos and selecting frames, and they're manually drawing bounding boxes and associating diagnosis with that, and also delineating the margins of tumors on the images as they see it. So these were expert clinicians from the San Martino Hospital in Genoa, which is an excellent referral center for this kind of procedures. So we got our databases from which we started then training our AI algorithms. And we got some very good results. We're still improving this. And for the detection, we are now using YOLO. There are different versions of YOLO, but we customized a bit our algorithms and train on our data set. It's getting quite good results. And this is for the automatic detection of the tumors with a mean average precision above 65%. And for the diagnosis, this is some classes that are benign lesions, and then SCC is the squamous cell carcinoma, which is a tumor. So you can see from these results that the algorithm is quite good on understanding that tissue is healthy, understand its tumor. When it comes to benign lesions, it's not that great yet, but we are looking to improve that. Basically, it's a deficiency of our training set that doesn't have many examples on those features, on those kind of diseases. And for the segmentation, here we develop our own customized deep learning network, which was based on the Deep Lab V3, and that's the kind of results we are getting. So it's a very good intersection over union, and performing, all these algorithms are performing pretty much in real time. And so from that, with those good results, we designed a clinical study and integrated everything into a kind of a clinical cart. As you see here, we call the VETA, and create a nice user interface for clinical use. And now it's in the hospital undergoing the first clinical trials. And the study is called ENHANCE, and it's funded by this project called RAISE. So we are having this machine there in the hospital, in the clinic, It's mostly collecting more data and assessing the performance of the system. And we're not trying to replace the idea is not to give direct feedback to the surgeon at this point, but we are assessing the technology. The next step will be to providing real-time feedback from the AI system, the clinician. And it's also being used in the operating room. So I don't have the picture here, but they also use it there. So now back to the surgical side. I just put this here to remind some of the challenges. So this kind of schematic of the surgical setup, been using this slide for many years, so probably Lourdes reminds it. And these are the challenges we identified when we first started working on this. So the need for a microscopic precision, the long operating distance, so they are guiding the instruments for 400 millimeters away from the target. The ergonomics of the setup is poor, the controllability of the tools are poor, and also the visualization for the microscope and the laryngoscope, as you see there, are not easy. Difficult access, difficult visualization. So it's a prime area for robotics, as we noticed many years ago and started working on this. And the first thing we did, it went through a few iterations already, is create a better system to control the laser beam. So this is one of not the latest prototype, but one that was tested quite a lot. We call it CALM, Computer-Assisted Laser Microsurgery. It's basically a small, relatively simple robot of only 2 degrees of freedom that moves a mirror, but with very high accuracy and precision. And we also added this new control interface. As you see here, it's controlled from a tablet, which turned out to be super intuitive to use. Anyone that has never experienced with lasers or anything can control the system, because it's just like drawing, and it helped bring a lot of the benefits of robots to this. I didn't mention the other slide. You also saw that you can plan trajectory and repeat all the functionalities from robotics can be added here now. And this is just a summary of the many trials we did of this involving the end users, so the surgeons. And we started with trials with some plaster blocks that we did in-house for precision testing, and then went to ex vivo testing on pig larynxes, which have a similar anatomy as the humans. And this we brought to several ENT conferences and set up this kind of simulated surgical setup and asked surgeons to test it. The result was always very positive, including tests on cadavers. So here you can see one of the tests there. So we are now pushing this forward towards the markets and trying to make this into a medical device. I'll talk more about this in a bit. In the meantime, we also started working with Karl Storz. Not so long ago, they came to the market with this exoscope, which is a imaging system, 3D imaging system with very high magnification, which can indeed replace the surgical microscope. So we saw the benefits to address another challenge, which is the ergonomics of the surgical setup, and start working with Professor Peretti, which is a main surgeon from Genova, and Karl Storz to adapt this camera to the transoral laser surgery setup. So this is one of the supports we developed, and then another one to have a clear view. And this actually was transferred to Karl Storz and became a product that they now have on the market. And they're also doing courses on this, so they call it heads-up transoral laser microsurgery. And this is how it's used on the OR now. So they don't use the microscope anymore, so they have this camera there, and everybody, the assistants, and pretty much everybody in the OR are using 3D glasses, because they see the big 3D monitor here for the image. But they still have the manual tools, the manual laser micromanipulator, the manual control of the forceps. So we really wanted to bring our CALM system to this, and this is one of the trials we did on a cadaver. And here's I was pretending to be a surgeon, being assisted by the real surgeons, and testing the system on a cadaver. So you can see some of the image we get, the 3D, and they put the goggles, you can see the 2D image. So also this was very interesting, so good results pushing us towards the market. and finally convince some companies to join the effort. And now LN, which is currently the #1 surgical laser manufacturer in the world, because Luminis is out of the business. Boston Dynamics bought it and closed that section. So, but anyways, they are interested in this, and they are now helping develop the medical device version of CALM. And this is kind of the setup we envision. How am I doing on time? Okay. So the other challenge was that the tissue manipulation with the forceps. So we also spent some time playing with little robots for this to robotize the tissue manipulation, and here some versions of it. And we actually accomplished, so having the robotic laser manipulator, robotic tissue manipulation, we can now have a system that can be fully teleoperated, and the surgeon can move even to a more ergonomic operating setup. So we actually did that and demonstrated on a telesurgery demo that we did back in 2019 with collaboration with Vodafone. That time 5G was still in prototype phase, so there was not a commercial yet. But we set up the system and demonstrated the possibility of using 5G for long distance, in this case, transoral laser microsurgery with our devices. And the hospital was 15 kilometers away, but was a nice demonstration. And this was just before the COVID pandemic, maybe a couple of months before the shutdown. And there's an auditorium full, like 300 people watching this presentation live. And I think, yeah, this image from the operating room. In this case, we did tests on silicone models and then animal tissue, like in this case was a pig larynx again, and then some cadavers. So this is the setup. Everything is controlled remotely by the surgeon, and here just some assistants. Basically, this guy here is holding surgical smoke evacuator, just basically a vacuum to remove the fumes from the laser surgery. Okay. Of course, there's another line of research that we started many years ago, because initially the dream was to miniaturize the entire surgical setup and bring it to a tip of a flexible endoscope where you could go near the operating site, and so to have a magnified view and control it. And we actually started working on this, and through a project called a MicroAlp, quite a few years ago already, where we created this flexible endoscope. We had a stereo vision, illumination, and a micro robot to manipulate the laser close to the surgical target. And this was the final demonstration of the system on a cadaver. And yes, we also had the surgeon console with a stereo vision, tablet interface for the laser control, and some augmented reality features to plan laser trajectory and control it from distance. But lots to talk. We continued the project and lots to talk about it, but maybe next time. I just wanted to kind of go towards the conclusion here, saying that all the technologies are presented first for what they call the free beam laser microsurgery are now being supported by another EU project. So it's a very large project, about 9 million euros and 12 partners that we are working towards bringing that to the first in human trials, both the AI modules and the robotic. So based on our lab prototypes, let's say, we are enhancing their technology's readiness level, so creating prototypes that can be tested in human, and towards the end of the project, we will be doing our clinical studies. So hopefully we'll be able to share very soon some nice data from there. So again, we have the ones technologies mostly based on AI for the diagnosis, detection diagnosis, and then the robotics and also AI for the surgery. And this is the team that is helping to implement this dream. What is next? So the next challenges is actually something that Professor Fiqueira here started about 10 years ago when he was still a PhD student in my lab, which is that on autonomous laser ablation control. So the idea is to control the third dimension of the laser surgery which means the incision depth. So now we're controlling the laser position and let's say in XY, the aiming of the laser, but controlling how deep it cuts is still a challenge. So back in the day, we were doing that based on modeling, so doing a lot of studies on laser tissue interaction. But more recently, we started looking into OCT to get the real-time feedback. OCT here can be really a nice technology because it allows us to measure the distance to the target, which can be used to better focus the laser beam. So to do a nice quality cuts, the laser beam has to be really well focused. So this provides feedback for that. We can also get information on the infiltration depth of the lesion, so the 3D aspects of the lesion, and measure in real time the ablation process, so the depth of cut, let's say. The problem that we are currently facing is that OCT data is really, really big and massive. So we're currently investigating some more like mathematical ways to compress the data. We call it compressed sensing, so which has shown some potential to speed up and be able to use all the OCT data in real time. Next challenge is actually couple everything that I presented before, the AI and the robotics, so the mechatronics of the AI systems, and make that autonomous systems for the controlling the laser ablation. So the idea is that you can detect the lesion with some AI modules and track while it's moving, if the patient moves or there's some physiological motions, and then you can automatically control the laser to vaporize that area. And so we did some experiments on that. So recently published a first paper on it where we were testing this solution. So with this, I finished the talk. Just wanted to show this picture, which is now a bit old already, but I like to show it because it shows the international dimension of the team. So we have people from all over the world that come to Italy to collaborate on these nice projects. And thank you very much for your attention. If you have questions,
Thank you very much for the very interesting talk. Okay, we're going to open the floor for questions now. Any questions, discussions, concerns? Yes. Yes, sir. Please go ahead. Wait, can you speak a little bit louder? I don't think we have a we have a microphone over there.
I can do that.
Okay, thank you, Ravi. Sorry about that.
Thank you so much for the wonderful talk. Really inspiring work here. My question for you is, you're looking specifically at the transoral surgery. Do you think that a laser scalpel could be used in other, other surgical applications, other parts of the body? We've got like a lot of the flexible robots that are taking, tools inside the body to like maybe inside the abdomen, and adding like a laser scalpel to the end of it. Those robots will be able to enable surgery on other parts of the body.
yes.
You still want to stay in your like.
No, thank you for the question. That's a very good comment. Yes, the lasers can be used anywhere and surely can be expanded to other areas. Actually, it's used in many other applications already. Yes. Also, with the Da Vinci robot, it has some laser tools. You can integrate laser there. So lasers are really, I would say, in my point of view, an ideal surgical instrument because it allows not only very high precision cuts, but also very high quality with very little collateral damage, little bleeding because of the heating. It it coagulates the small blood vessels. So there's reduced blood loss. and also can be coupled with optical fiber, so it can access very difficult regions in the body. So for sure, all this can be then translated to another area.
Thank you very much. Do you have a follow-up question?
No, we have a question that asked a follow-up.
Yes,
but
please,
no
go
one-
ahead. In the meantime, may I ask Dr. Paul, can we start switching laptops? Thank you. Yes, sir, you'll be go ahead.
Oh, sorry, so I had a follow-up on that. So just to do that in your reality, what are some of the challenges that are in the way that still need to be addressed to take a laser scalpel, autonomously perform surgery and other like, soft moving?
Autonomously, yeah, you need mechatronics to be able to control this laser scalpel. And then depending on the necessary quality that you need in the surgery, you also need to take very good care of the focus of the laser and then delivery of it, because otherwise it just burns everything and it's out of focus. It basically carbonized tissue and then does not cut. But yeah, if you have the robots that can manipulate a laser beam, so that will be the first thing that needs to be implemented. And then adding, for sure, do it autonomously, you need to add intelligence and AI systems to, like I was trying to present, to understand where the disease is and how to control the motion of the robot to compensate for tissue motions and tissue deformation also while you're operating, because when you cut it, everything starts to deform as well. So it's another challenging aspect.
Thank you so much.
You're welcome.
We have time for one more question. If you have any. Yes, please.
Hello.
I think you have a really nice example. Talking here, like sort of like translating in terms of research that you do in the lab and taking it from the hospital for further.
I guess the strongest insight is that the clinical need and having clinicians that help you sell the idea to the companies are key. In our case, we really work with an opinion leader in this field, and he's kind of driving the development, but also the technology translation. And having a researcher tell a company, yeah, you should invest on this, it's tough. But if the clinician is actually saying, this changed my life, this is so much better than what we have now, it will be a killer product, and then they start listening and start investing on this. I guess that's from what I saw recently, also the interactions with Carl Storz and other companies. It's needed, I think, is without that is super difficult.
I'm gonna keep you there just one more minute.
Yeah, sure.
Can you tell us a little bit more about what commercialization model you guys are using? Seems like you're working a lot with large companies. So are you pursuing mostly licensing of your IP or?
Pursuing different routes. So one for sure is licensing, technology translation, but also a startup. So we have a part of the team. There's some people interested in creating a company to bring this stuff to the market. Also, the surgeons are involved in, especially on the AI system for this disease detection diagnosis. The surgeon is highly motivated also to create a company on that. So we started the business plan development and these things. And in the end, I think it's difficult. End up being easier to translate to the larger corporation, but then to create the value of the technology, maybe we're thinking to start with a startup, then it can be bought easier for a company. Also for companies, from what we learned recently, it's easier to buy a sort of a product that is almost ready to go to the market than to purchase research results that they still need to invest in more research and development to transform into a product.
Thank you very much. Dr. Matos, please, our speaker.
Thank you.
Okay, let's find out if this goes. Okay, it looks like it actually might work. Good morning, everyone. It's really nice to be able to chat with you. Thank you for the invitation, obviously, to come and be able to speak with us. I think this talk comes, it's almost like I couldn't have planted the questions better that just came up about what other options there are for laser-based surgery for tissue. So I really appreciate those. And Dr. Matos, your talk was phenomenal in terms of the fusion of these sort of robotic systems, laser systems, treating tumors. This is perfect timing for kind of what we're going to dive into here too. So for those of you who don't know me, I wear two hats at Duke University. I'm a full-time clinical neurosurgeon in practice at Duke. I specialize in brain tumor removal. So half of my time is spent in clinical practice taking out brain tumors. And the other half is guiding the Brain Tool Laboratory at Duke, which is really a translational engineering lab trying to solve problems that we're seeing in the operating room with technologies we can develop in the lab. And a lot of it has come down the road of we're starting to get automation, sensor fusion, robotics. How do you take out, lesions for us? Because I sit in the world of neuro, trying to think of like, how can I do things taking out tumors inside the brain? But really, someone asked a wonderful question, like, can you do this in other parts of the body? Can you do this in other tissues? How do you develop systems to treat diseases in the entire spaces of the human anatomy that we have to deal with? And so that's some of the stuff that we're trying to think about is how do you mix sensors, robotics, and sort of techniques to manipulate tissue. And I think it's, I'll get into some of this here, I guess, there. So I guess I'm supposed to give my disclosures. None of them really have any relevance to what's going on today. So really got to start at the beginning because, as a surgeon, I love thinking about history. Because if you think about it, we're going to be sitting here today looking at the most advanced possible tools that are going to be applied to the human anatomy for the next 20 to 30 years. We're like pushing that boundary, but you got to remember where we started here, right? So if you go back like 2 millennia, 3 millennia beyond, we're banging rocks and sticks together to try to get things out of the human body to treat disease. What we are really in the business of doing here is developing tools and technologies that let us treat human suffering in the best way that we possibly can. That's it. And it's either with rocks and sticks way back in the day or an evolution of tools that have occurred over the years to now. What we're trying to do is how do we take all these advanced technologies that we have now and do the exact same thing? So that's the fundamental thing that we're trying to address with all of this. Now, it started now from the neuro world. Obviously, we found skulls back in the prehistoric times with holes in them where people have tried to do things within the head using just the basic tools we have around. Everything evolves over time, including scissors, saws, drills, bits, hammers, everything you can get your hands on. We evolve these tools in a various way. Now, this one, I just want to point this out because it's just to give you a sense of like trajectory here. This is something from Diderot's Encyclopedia in 1772. Do you see how it's got like a twist crank drill? Like one of these things that you might see in wood shop? Just keep that in mind, okay? So that's back in 1772. Now, if you go forward, when I graduated from neurosurgery residency in 2015, this was a craniotomy tray that I used to do trauma neurosurgery up in Boston. So, and I just want to point out, you see this device right here at the side, the same twist crank drill from 1772. This thing, they gave it a fancy name called a Hudson brace, but literally it's the same thing. So when we're thinking about like why is that even in my tray? Dozens of 100 years later, 200 years later, it's because what this is actually doing is it's solving a problem. And this is what I have to ask whenever you're thinking about how you're approaching your technologies, how you're approaching the surgeries or medical applications that you're doing. You have to think about what's the fundamental problem you're trying to address. That's what builds everything. I know it seems like a broken record, but what we're trying to address is how do you get inside the human skull? That's the problem. It's a hard thing that is attached to people's necks, and you've got to get on the inside and get through this to get there. So to do that, we have a hand crank drill because it actually turns out it works pretty well. But it's not the only way. And so when we're trying to ask these questions of like, how do you actually manipulate these tissues? You could already see in Dr. Matos' talk earlier about how you start layering up technologies and approaches to address certain questions that you encounter along the way. So now, and the other part about this I just want to bring up is, I'm going to zip through some of this history, but things evolved obviously since we're just, hammers and nails, and we sort of have more advanced electrocautery. We have imaging systems. We have robotic systems coming into play. We have all the technologies that are starting to layer up. But the reason this is occurring is because we're doing stepwise fashion, asking these fundamental questions and looking at seeing how we can solve them. Now, this is maybe perhaps a bit more 30,000 foot than anything at the moment. We'll get deeper into some of the technologies, but I think this is the best thing that I can convey to you is sort of a way of thinking about some of these problems rather than my particular solutions. And one of the things I want to just remind, especially when you're working with surgeons, is the technologies, the tools that they're using that are sitting on their table, on my table in the back of a craniotomy for tumor. These are instruments that evolved over the course of that 2,000, 3,000, 4,000, 5,000 years beforehand. It isn't handed down from above as the only way to do it, but it comes from historical context. So if you think of just the instruments on the table, if you look at straight scissors or forceps or anything, you got to ask yourself, why are they straight? Why do they cut? Why do they have little rings on them? Well, it's because I'm a monkey with 5 digits at the end of 2 hands at the end of my arms. I have to have some way to manipulate tissues and cut and move. So we put rings on them so I can hold them with my hand. And they're straight because most surgical approaches up until more recently with endoscopic and minimally invasive techniques are open approaches where someone has physically opened the body and has a direct line of view from the outside world to the inside world. And so the instrumentation is linear. So you have scissors and pickups that are straight. So when you're thinking about redesign or asking yourself, how do you design something better around this? Go back to the fundamental principle of what is actually trying to be achieved by that instrument. That's the basic question. So it's not, and so when I'm a broken record when I think I've said this, but our job here is not to design a sharper pair of scissors. Our job here is to ask the fundamental question of what that scissor is being intended to do in the first place, and then develop the tools and technologies from there to accomplish that task in a more minimally invasive way that has less disruption to the patient and their tissues to ease suffering. That's it. So when it comes to those scissors and those pickups, just you say, well, maybe we don't need to do that anymore. But you can see how tools have evolved in the same mindset. Like you look at Da Vinci tools that are straight, the scissors, the graspers, and everything, they are linear instrumentation coming in ports from the outside to the in. They are built sort of on that historical basis. And you'll see that even in minimally invasive endoscopic tools, like this little graspers and scissors, people trying to get like making like 1 millimeter biters that look very similar, trying to miniaturize or automate or things. Just be aware of like what the fundamental task you're trying to accomplish is. I'm going to kind of go in a route. So I'm going to take a little bit of a pivot in terms of what we're thinking about in terms of our own sort of tool development, because from this, I'm going to move into a different space, which is really how we have started to ask a similar question like Dr. Matos and a number of people around the world and in this field is like, how do you actually enact the act of surgery on tissues in a more precise way? And so if you were trying to like break surgery down, back down to its fundamental questions, you're like, okay, if say I have like literally today across the street at Grady Hospital or up at Emory, you're going to have someone walk through the emergency room with a brain tumor. That's going to happen today. And that could be one of your family members, and God forbid it's one of you. But they're going to walk in the emergency room and they're going to ask, oh, well, help me. And so how are you going to do that? We need to get that thing out of their body because it is going to cause them suffering and disease. And so the question then is, how do you do that? So we need to somehow know where the tumor is, get to it, remove it safely, get out, let them heal, and get them on in life. And so that's the basic task. It doesn't matter if I do that with a pair of scissors or a robot shooting lasers. The question is, how can I do it in the best way possible? So as we're evolving and building this up again, the idea is to like every step along the way, identify the basic kind of like the fundamental question trying to ask. So for us, when we try to ask that question, just as a thought experiment, we just say, let's play with this idea. How do I remove a tumor? We started to go down the road of like many people are sort of converging upon sort of automated, how do you automatically remove this mass without the conventional need for mechanical dissection, all the trials and tribulations that come with moving these tissues around. We just played with the idea of let's do it in a closed loop way. So if we wanted to do that, so automate the whole thing, push the green button, make the tumor go away, something sci-fi. To do that, you start breaking down the problem from there. So how do I address these fundamental problems? Well, I got to know where the tumor is. Or let's say I need to be able to remove it. So I got to actually get rid of the thing. We've also been looking at like, how do you use laser systems to remove these tissues? Because the fundamental questions that we need to do when we take out a tumor, we have to cut the thing, get the actual mass out. We have to stop it from bleeding because it's going to. Things shift around and bleed and get very messy in there if you don't. And actually like volumetrically remove a tissue. It has to be out of the body at the end of the day. So say, okay, for us, the tool to do that, I mean, yeah, we could bring in the scissors, we could bring in the cautery and other things for one aspect of tools. And there's a lot of other interesting tools. Like I see Megan here in the audience, ultrasonic aspiration and like ways you can vibrate these tissues and cause them to disappear, incredibly powerful. We chose to navigate in the sort of automated space around laser tissue interaction. So like, okay, say we're just going to use a laser. Let's use it as a tool. We're going to use a laser, but to know where we're going to shoot that laser, we have to know what we're aiming at. We have to know what is tumor, where it is, and then shoot it precisely so you don't blast away something you're not supposed to. Over the last probably 10 years, we've sort of evolved a system to do that, starting from a very bare bones idea of just this idea of like, look at it, shoot it, look at it, shoot it, look at it, shoot it. Then we started back in the day with this basic thing. It's very simple. There's a CO2 laser up here. There's just a pointing guide laser. There's a little triangulation sensor, which is an MTI that maps out the surface of a structure just to know like a topology that we're going to aim at. Pipe that all down the same optics and shoot something over in this gray space over here. I mean, obviously no one's going to put their head in there anytime soon to have a tumor removed, but it was the basic idea of combining laser energy as well as sensing systems. Now, that sort of evolved over time through these sort of incremental steps because the fundamental questions keep coming up. Well, can I know the three-dimensional surface? Can I know the depth? Do I know what I'm looking at is actually tumor? Each of those questions creates a technology or a step along the way that layers up. So we added on stereo vision. We put in OCT imaging on the surfaces here. We actually created one of the big pieces, and we'll get into this a little bit more, is we created something called the tumor ID. Because we came into this issue, like if we're going to have this system that's sort of hovering above a surgical site, which is a sterile field. So again, this is sort of considering your design parameters. We're going to be in a sterile environment. I don't want to be, I would ideally not like to have to touch the sterile field at all in some capacity. I don't want to have to interact with it in a way that's going to contaminate it. You can design things around that and create cheese and all the things. But we said, like, can we make it just optical and without any contact, with any exogenous dye? So turns out tumors can autofluoresce, or they don't autofluoresce. They have an endogenous fluorescence that can get triggered by shining a particular wavelength upon the tumor. And so when you record the fluorescent light that comes back, you basically shine the blue flashlight on the tumor, look at the reflected spectra. We can piece through the spectra and actually classify the data that's coming back as either tumor or not. So that was a powerful opening for us in terms of answering that question of what is tumor and what's not tumor. Because if you're going to be shooting stuff, and especially in an automated way where I don't have my eyes, which have been trained over decades to look at what is tumor and whatnot based on white light visualization under a microscope, when I'm not the one just looking at that, some other aspect of sensation has to input that data. So we use this tumor ID system, and I won't get into all the details on that, which I'll get into some later on, but we were able to, this turned out to be a very powerful way just with spot size to map out these tumor regions. We'll get more to it. And then if you integrate all these things together, like you're hearing, is like the integration problem bringing this all together is then something that we can start to do. So I'm going to just dive in a little bit more into that tumor ID component. So zooming in even more from the space of like, here we are trying to develop this thing to remove tumors. I'm going to show a project that was sort of worked on in terms of utilizing that tumor ID system along with the laser system to ablate the mass. This is something called tumor map that we created. Done by this is a work by a lot of incredibly talented people. Dr. Guangshen Ma there here in the back. Guangshen, you got to hold up your hand. I'm going to force you to do it. Yep, there we go. That's he really pioneered a substantial amount of this work and is now working with Dr. Drelos up in Michigan and Ravi Prakash here, who has done incredible efforts on both of this. They tag teamed this for a year, 2 years, longer, probably longer, to get everything put together. But they did an incredible job. But I wanted to highlight kind of what that actually means in practice then. So you have this tumor ID system and how do you integrate it? So here's the basic idea. And I would just focus over on the right there. So if you want a mouse, okay, we for grant asset like annually related tumor, we started a mouse model using sarcoma. And so the reason we're starting that it has a point to it. One is that it has you can do repeatable types of tissue of tumors over and over again, and it's mice and they're reproducible. The other thing is it's very visible, it's in a web, so and it has a margin. So we can not only access the tumor mass itself, we access it, but we can also do margin resection, which is a very big part of our figuring out how to identify what's tumor and what's normal. So we have access, so we have these tumors, this sarcoma, this little marrow mass, this tumor here. The idea then with this sort of integrated system is you take a kind of building on this idea of casinos is already becoming increasingly popular for this because of the kind of precision of surface. We can take an OCT map of the surface. This is purely, we're kind of like butchering the nuance of OCT to create the surface profile using it. I mean, there's obviously a lot more you can drag out when you do OCT technology to this that, but we're starting with that space. Create a 3D surface map, use the tumor ID to search out the area, classify what you're looking at as tumor or not, create a map of the area, and then use it later to see back. The similar idea of like a closed loop system, where you have an imaging system, then you use a laser to later. So this is just, again, like it's in line with, you're asking the question, like, can you use other tissues, other tumors? And yeah, we absolutely can. This is probably a very similar thing. So I'm going to move on to this just to give you an idea. So when we were starting this project, and this is probably worth talking about, because anybody who's going to go into this space of using some system to identify what is tumor and what is not, if you're going into an oncology space, especially in robotics, you're going to run into this problem. And the problem is, how do you know if you have such precise optical or some sort of mapping experience, so like some sensor is identifying a region as tumor, doesn't matter what it is. Say it's my tumor ID sensor, say it's a visual identification, say it's some mass spec, Raman, visual light, anything at all that you can think you can interrogate the tissue and it's sending you signals back and you're trying to say, is this tumor? You have to validate that somehow. Like you have to say on real tissue, were you right or not? When you're doing all your classifications and you're collecting all the data, you have to be able to say, is this actually tumor or not? So we likewise run into that problem where we say, we have this tumor ID system, and you would rightfully ask me, well, how do you know that that's actually tumor? Like you've got these spectra and you say that it is, like, why should I believe you at all? Like you need to prove that to me, like that there's actually, that what you're actually shining is actually tumor. So the challenge is the gold standard is histology. We're from now we start wandering into the pathology. So if you have tumor inside of tissue, the way, you're probably very familiar, but if we're trying to identify as tumor, you got to cut that tissue, you got to stain it, you got to identify all these molecular markers that classify something as tumor or not, make that area show up and be like, that's a tumor and that's not. So then you correlate that with your data that you're getting from your sensor and you validate the sensitivity and specificity of your sensor to identify what it is. The problem with tissue is that, just like we've seen, it moves, it bleeds, it shrinks, it expands. And this is the challenge with validating any sort of imaging technology, is you have to identify where you shot in histology terms. So you have to line those up. And people have looked at a bunch of different ways to try to do that just from other imaging modalities being used to validate that. But really, it comes down to histology. And so the best that we have come up with at the moment, and I'm all ears for other methods, is literally marking. So when we're doing a tumor ID sample, this is just to give you an example of this. Here's a bunch of tumor samples on the left. We've literally marked with pathologic. There's a dye that's used in histopathology and like in the anatomical labs where you mark it with like a paint. It's not anything fancier than that. It has some, I mean, it's all expensive, but that's all it is. It's a paint. So you have a paint that will stick with the tissue through all of the sectioning. And so essentially you mark where we're actually sampling, split the tissue in such a way as to then be able to, I can actually go to the next slide here and show that. Oh, is it? Yeah. Actually, this would be a better way to go. So we monitor an area, we label that tissue, we section it directly along the line, horizontal to the surface, flip it on its edge, do the sectioning, process it through the histopathology. All that to say is the reason we're doing that is because then it shrinks. The idea is that at least once it goes through all the formalin and all the shrinking and the alcohols and everything, it will shrink proportionally. That's the assumption, it's something to worry about, so that we can then mark it out. And so then on all these histology slides, when we're trying to validate the technology, we're looking, we have a pathologist that then goes through and looks at it and validates where we're looking at the point and not. So I only bring that up in that we have validated this tumor ID system in that method. There are inevitably errors in it. There's things about depth of penetration that are going to be things that we have to work through. There's area of like the area of the dot itself that we're sort of revising, but that's the sort of approach that we've used to identify where is the tumor and where is the healthy. So there's the beginning of one. The red stuff, muscle fiber. So the trouble, and I get this question a lot with this approach, is what do you do? And this is a bit of a wander, but I'll bring it back to what we were talking about. What do you do on the red line, on the margin? I got that question several times this year. It's like, how are you actually identifying right at the edge what is tumor or not? because I want to just convey it to you for anybody who's going in the space of oncology. That is, we have in our minds that there is a margin, like it is a 0 and a 1. Like you somehow cross a boundary from tumor to normal, and it's like this clean line that goes right down between those two things. Even medically, as we approach that in surgery, we think of it like that. We're like, okay, we got to get to a negative margin. In practice, there is an invasion zone right at the edge there. Because for us, we're starting to find this in like spectrally, we're seeing that there's actually a subtle invasion zone. So if we're thinking about like margin identification, these things come into play now because you're suddenly getting the precisions down to such a level that you have to think about it. So I can go on and on about margin and that, but I wanted to show what this actually looks like then in practice when you bring all this together. So you bring the imaging system, you bring the laser system, and then actually perform a ablation. So this here is an OCT surface map of a tumor. You'll see this on the left. Just gives you an idea of like once you start doing these loops and bringing them all together. So we map out the surface. We then take the tumor ID system, map out the tumor using the actual spectral signatures where we say, hey, is this tumor, is this not? You have these maps that are gradually getting more constructed. And then finally, you use, when you have this map, you can do the actual precise removal of the area. This is a thulium YAG laser that we're ablating the area that we had identified as tumor, and is doing so in a kind of following the contour. So when we're asking this question of like, can you create these closed loop systems where you're integrating sensors and lasers? Yes, you can. And it doesn't have, you can do it in all these different tissues. It's just a matter of layering up your sensors. Now that tumor ID system, we've done it ex vivo in a bunch of different tumor types and patients. I've actually used this, we've got it onto the sterile field. That's me doing a craniotomy. We brought it up onto the sterile field and actually using the system in the OR in live patients. Some not seen here is the open head where we're actually imaging inside the person's skull. And this was work that was really pioneered by a phenomenal MD PhD student in our group, Tanner Zacham. Now, looking forward as we're kind of moving this onward, it's that whole integration and mobilizing it so it can be in the operating room space and make some sense. So we're integrating this so we can have all these components compiled into a single space because we need to get this thing into the operating room to be able to navigate around that environment. We have to expand our OCT views and make sure we can get a bigger field of view instead of a tight, narrow 10 millimeter by 10 millimeter view that we have currently for the mapping that we're doing on these small mouse tumors. So we're doing work in terms of how you stitch OCT volumes together to create bigger maps. And then we're also doing a lot of work in terms of mapping the surfaces and the careful controls that we're doing, sort of modulating exactly where the laser aiming to the surface, because we're not dealing with a perfect plane when we're shooting a laser. We have to deal with normals as well. And so we're trying to optimize the laser angle. So just like Dr. Matos was talking about in terms of like delivering laser energy and how much needs to be delivered to perform an ablation, we're modeling both the positioning of the laser itself, the entire system relative to the surface that we're scanning, and also doing that in simulation to kind of do training and optimization of laser energy delivery. So I'm not going to go into all the details, but we've been working with Duality AI for some really powerful modeling in terms of laser tissue interactions. This is the sort of more fancy graphical output of it, but on the back end, there's a lot of modeling of laser tissue interactions, energy absorption, and cavity creation that we can iterate and do some predictions about, like if we're going to shoot the laser at a certain amount of energy, what's it going to do? Knowing that we are also in an environment of inhomogeneous tissues. So like it isn't, all tissues are not made equal. And so we have a bunch of different things. It could be everything from a tapioca pudding to a racquetball in terms of thickness or firmness. And we have to be able to adapt in real time and learn as the thing's going. So there's an adaptive component that's part of this process as well. We're also doing some, Vincent Wang and Leela Bridgman are collaborators of ours, have been doing some awesome work and sort of using MPC controlling to figure out, to also model some of the heat spread for energy delivery, depending on the different types of laser energy we're being put out there. So these are just ideas, you know, this, and the whole point of all of this too, is that as you see, we've gone from basically rocks and sticks to how are you doing layered, nuanced, like controls and robotic systems to create a removal of tissue. But the whole idea here is just all the different components that you need to add to this to build up a system that can perform safely the task that you are fundamentally trying to achieve, which is remove this tumor. That's it. So all of it is just built to say, what are the ways we can do this in a safe way? And it takes an incredible amount of effort. So I know I'm sort of running out of time and I could talk for hours, but you don't want that. This is done, this has been a fraction of the many incredible people that have helped input onto this project and continue to collaborate that we've been really lucky to work with. And it's obviously, as you can tell, it always is a team effort with these things. So I'm going to pause here and see if anybody has any other questions or concerns, worries, cajoling that you'd like to throw out there. But thank you for your time.
Thank you very much for your very insightful talk. I think we already have a question here.
Yes.
Thank you. Very interesting talk. Enjoyed it a lot. I have a question about usually the role of tumor is used in combination with other therapeutic approaches, some form of radiation, for example. So, and potentially, chemotherapy. So, are you looking at the efficiency of these techniques in terms of how much they save you? Additional radiation therapies, for example.
Yeah, I think that's a really insightful question too, because it takes into account that because I have a hammer, so everything looks like a nail. So you're like, okay, it must be surgery, it must be the way to go. No. So like you have to realize like that's exactly what you're pointing to. It's an entire constellation of things. The question, it's an open question. Say like, what role does this type of tool, and that's all this is. I can make this as fancy as I want it to be, but ultimately it is just a tool. What role does this tool have in the constellation of treatment care for a patient, say with breast cancer or with prostate cancer or some glial tumor or anything anywhere in the body? And right now, like with this sort of resection paradigm from this, you're not going to be able to resect a mass the size of my fist anytime less than 20 hours later. It'll be maybe done. So there's going to be some combination of contemporary technique that's built up with some assisted tools, maybe on the edge of the boundary, that might actually reduce the need for adjuvant chemotherapy or radiation some fraction, if it were to say improve the extent of resection, meaning how much you get out. Maybe you do need less timing around particular chemotherapies. But we would never know that until we start to go through that process of improving it. And this entire bit is built historically on the idea that surgical resection provides benefit. There are some tumors where it doesn't, in which case it would not make sense to be applying this at all because you have these other technologies. But if it's when we sort of think in the space of like, because it goes down to the question of like, why are you doing this in the first place? Like, why do we even open someone up and take that tumor out to begin with? Because it's a risk. It's built on that. The clinical data that exists up to now is saying, hey, if we remove that, people seem to do better. And so we sort of build on that and say, well, maybe if we can improve that extent of resection, they'll do even better than that, along with all these other therapies that they need. So, yeah, thank you.
Thanks. Excellent presentation. With the technologies you're showing here, are there tools or sensors that have some limitations in terms of how far they are away from the anatomy? Right, you talked earlier on about trying to stay outside the surgical field.
Yeah, so in terms of like things that we'd want to get if they're too distance from critical structures and things. Yeah, so this is a big part of like when you're actually operating. I was like, can you anticipate where a nerve or a vessel or an artery or something is amidst those when you're operating? It would be incredibly valuable to be able to have real-time feedback of what's occurring on the other side of a blind corner or a deep tissue in the current manual world of dissection. So if I'm like cutting my way through a tumor, I mean, there's a carotid artery running through the middle of it. I'd love to be able to know how close I am, which we can do in part, but as you were watching kind of changes in tissue or having real-time feedback would be very valuable. But that's a big limitation currently. And so it's a combination of like, can you time different sensors and other aspects, or even just pull data off the tools we're actually using to get that data would be really helpful.
Very well. Please join me in thanking Mr. Finger once again.
popular language model. Yes, and then basically the first thing with the model is that it can be trained from raw text and basically you can buy a lot of them on search. So that means they have really much amount of data they can use the train model. And they so with that there's a pretty strong generalization of it. And that really is what we need in certain labs. We always have to the data that we have are quite like limited in size, and so that the generalization of the model we have to train is not good enough. So that these elements. And also there's another the language model is we try to use the text into the so that it can better support the communication across different modalities or across different like agents in the system. So for example, you know, so that's different things I see from vision language model and that so that there's another thing. This is about why surgery we have so many raw data that we already haven't been used like for developed AI technologies, for example. So every day surgery. Nowadays those videos have been already widely used in many procedures. So there are many videos being used or recorded in the hospital every day. You can find like teaching materials or videos online for medical students, and those data are coming with video, image, and also text and audio together. So we can also support the video language model training, and also there are already some disease teams where label the data sets, although their size are relatively small, but they have pretty good labels. Then if we can find a good way to integrate all those data together, maybe kind of raw data, but like can integrate that and train a more generalizable model, then it will be better for surgery, like understand surgical thing. And so that leads to our first work trying to benchmark the PLM on surgery. So our logic is the ultimate goal is we want to find a better strategy that we can train those language models prior to surgery. The problem is we feel instead of just directly deciding to integrate those data to try different training strategy, the thing we want to do is first see how good those models are on the surgical data. So which the benchmark. And then the goal for this work is we are trying to see if we can get some insights for some long-standing and solve the problem, like explainability. Meaning surgery is a long tail, like data. So there may be many quite frequently, but the event itself is rare and like for example severe you may not see many data during the training, but like at testing time, if that happens, can we know that when it happens, the model may not be able to see like understand type data because they didn't see that a lot during training. So that's kind of our focus. And there's already one work doing the related benchmarking work of BLM for surgery. And so for here, if you look at the white and black bars, they're task-specific model, meaning those models are more trained with the standard strategy. They train on well-labeled task-specific data set. And the white bar, the training and testing data, they come from the same data set, so similar distribution of visual data performance. And then the black bar is they train on one surgical data set and test on another one. So there's a distribution. And then so they call it sort out of domain as the meaning says. And you can see there's a big drop in the performance of the black bar because the generalization ability is limited. And then those color bars are VLMs. So if you compare it with them with the black bar, their performance are actually pretty like generalization performance are they kind of comparable to the black bar.
The problem here is actually, if you predominantly look at the first task, full recognition. The score there is actually mean average precision. And the black bar is around 0.3. So it's quite low. And means all those colorful bars, their performance are also low. So those models, although they show good generalization of it, they're still quite far away from the practice. So the one thing we will try to explore is there any better way that we can train those models to can be like better used for surgery. And also there's one interesting thing on their work is the magenta bar, the search field is a VLM model pre-trained on a large like cyclical video data set. And then if you see its performance, sometimes it's even like worse than ChatGPT and Gemini AI, which is not specifically trained for the surgical data. So it means we do need a better strategy to do this. And then so that leads to our very initial exploration of this direction with my incoming PhD student. And then so the figure here is quite a popular VLM model. So the high level idea is the text encoder and imaging encoder together forms the model. And then one side is they input a series of text prompts into a text encoder, extract some text features, and at the same time, they input the image to the image encoder, extract some image features, and then just compare the similarity between them. So S here is the cosine similarity, and higher means these two features are more similar to each other. And then if we want to do the classification task, we can by the instrument responding to the highest S score as the classification results of the model. And that's the model itself, is our contribution. And then our goal is we want to analyze where which part of this model goes wrong, so that potentially we can how to estimate the uncertainty of the models. It's more like an expandability problem. And then so the strategy we decided to use is to visualize which part of the model, which part of the image that the model is looking at when the model is doing prediction. And so we adapted the method called break-can. Basically, the high-level idea is, let's say, if we want to visualize the model's attention map related to hook in this example is +1, so we found it as 1. So our strategy is to extract the feature map from the last convolution layer of the image encoder, and then review the value in those feature maps as the model's attention relevant to where the model is focusing on. So to get the attention map, we basically will weighted sum of across all channels of play. The question is how to estimate the importance of each channel. And then this method basically use kind of calculate the gradient of the model's output with respect to each feature channel. So the intuition we have is that larger gradients may indicate the feature has more importance in the influence the decision of the model. So basically calculate a derivative and average the gradient in that channel and use that as the weight for that channel's feature map and do a weighted sum get attention. And then here I will show 3 examples, actually quite typical examples see across the whole data set about this. So basically here is here is one quite relatively easy image, and then we input into the model, and the model tells us the class of instruments have responding to the highest cosine similarity score is hook. And you can see the white word kind of on that side of the image, that's the hook. So the model is doing the correct classification. And then we extract the attention map responding to that instrument. you can see there's a highlight, it's actually aligned with the tip of the instrument. So in this relatively example, we can actually see the photo is actually looking at the right positions when we can make a prediction. And then there's a hard example here. The background is kind of messy. And then you can see the tool is like inserted from the top right corner. There is just very small part of the tool is visible. And then we check the model actually tell us the grass curve is running about items that is similarity. And then that's actually wrong because the tool here is hard to see. So the green box there is actually the branches and it says that it's a the model predicts saying this is the bad catch. So the prediction is wrong. And if you check the attention now, it's basically randomly looking everywhere and doesn't really have to relate to the high score or the tour. So basically meaning the model may kind of by this image. So we are thinking if we can like the kind of information that happened to and maybe predict and what situation the model may not be very like confident about its output and potentially goes wrong, then it would be quite interesting. So that's one of our future plans based on this work. And also there's another interesting finding. So the previous two examples are from general purpose video, and so basically they didn't really need to train on surgical data. But this one is the search video, the one I just mentioned. It has been like a trend on a large amount of raw surgical videos. And now if you look at its prediction, it makes sense. Its prediction is pretty good because it's kind of finding the trend of the surgical data. So it makes sense to get a good prediction. But if you see the attention map, that's a like consistent pattern we see across the whole data set. We didn't see the attention is kind of related to the tour or related like overlay with the tissue that the tour is interactive with. So one of our hypotheses is that this model is pre-trained with raw videos and then without special supervisions or objectives, encourage the spatial reasoning. So it's possible that's the reason, but like one of our next steps is to verify that this hypothesis and also to figure out that way to design like a study. Now, go back to these slides. I'm actually not fully groundwork. I'm here working on the program that I started to think about at the beginning, the truly multimodality program in medical areas. Can we like explore different types of imaging data or other non-image data to get a better understanding of surgery? And then, so I worked with Brad and Patrick at university about trying to like better understand the OC data to help the robotic control of laser scalpel. I think the both Dr. Magnus and then Dr. or the kind of data. So the generic here is lasers where they can quite accurate targeting, right? But you probably need a better feedback for the like surgeon need a better feedback so that they can understand, they can know how the tissue is response to the laser targeting. And then the program is laser targeting quite like high resolution, millimeter, and we have a good enough image and modality compare the same sub-millimeter accurate perception. So right, and then also it's quite suitable in the because it has extremely high resolution. And then another motivation is both the OCT and lasers where they are kind of targeting using training, so it would be good if we integrated into the robot and make some control and make them multiple size, and that's another motivation of this work. And now, generally, how OCP is formed for those who have not used the regular, not very familiar with that this modality before, same as you actually, I'm new to this area. And so basically the general here is first, those OCP scan and, for A scan, basically it's a one scanning of the depth profile of the suit, and then they splitting the A scan, I put them side by side, and then they can form the 2D scan, and then stack the 2D scan to the 3D scan. And then so you can see those scanning is kind of discrete, right? And then the problem is when we use those imaging data and do the surgery, we probably want to continuous reason. And so the problem now can we learn a continuous reason from those discrete data? And then, so there's one method called neural vertex cleared from the general imaging called the nerve. And to be honest, it's kind of an outdated method for the general imaging. But we still find that it's really a good fit for our purpose. Like we try to learn a continuous representation of OCP data. And because I think I'm running out of time, so I'm not going to into the detail of this method. And then basically what we are doing is we adapted the model. And then now basically we learn continuous function takes a X, Y, Z of a point in the volume, and then you can output the intensity of at that point. Basically, with that, we can learn the information of the whole 3D space, actually the 3D volume of the tissue. And then with basically for this work, we thought it's easy at the beginning, but it actually took a lot, like quite a long time for us to get this model to converge to those OCP data, because it's so noisy, not noisy than like those general like images for real life. And the superstition of images, sometimes, many times they are noisy, sometimes they are clear that so people use the model. So we did some modification on the model. Finally, we converge. So here the first column is the ground truth of B scan, and then the next two columns, the first one is our comparison method, also a method to adapt nerves to learn the CT scan and MRI with volume. And then basically it just doesn't converge. The quality of the image is not very good. And after like our modifications on nerves, and we converge on those data. And then we are here actually that's potential like direction of this method that we are open like the discussion with people and collaboration, we are interested. And but one direction we have been thinking about, Dr. Colin kind of mentioned it, is the OCP data, they have quite limited field of view. So if you want to like do some operation on a relatively large area, you may want to stitch in those OCP data. And traditional method is more like do the feature matching and do the registration, can be kind of time consuming. And so one good thing for the nerve is like a differential or continuous function. So potentially can support better registration. And also it can just be like, we can just train one nerve model with multiple OCP scans, like multiple overlapping OCP scans, and then make it just like combine those information together. And also one contribution of our work is we make the training of the model in real time, but like we basically go a year from instant NGP really fast rendering for the like the general images, and we take part of the model integrated with ours, and we can achieve a like and training for this. We just need the information of the issue. If we need more, it's more like it's always around like less than 1 minute, so it should be pretty quick for our application. So those. And then, last thing is I want to kind of introduce my lab. It's a new lab, just 5 months now. And then we have our focus is one perception and calibration, and we are also going to use the perception to do the planning and control of the robot. And also, I feel there's a big part that's still missing in the current community is like have we consider the patient outcomes, also consider the surgeon in the room when we design those algorithms and devices. So we will also involve some human factors in my like research focus of my lab. And I have 2 PhD students coming and 3 master undergraduate students. So we are still hiring, and please keep an eye on our posts. Thank you.
Very well. Thank you very much, Dr. Lee. Are there any questions from the audience? Yes, we do have a question on here.
Thank you for your talk. I was wondering with the attention maps, are you just applying those postdoc to evaluate why your model decided in the way it's decided, or is it also used actively during learning? Somehow to postdoc or active methods.
So I didn't really catch.
No, you're right. For the attention maps that you showed, where the model attended certain areas when it's classified the book, for example, are you just using this after your model has trained to see why it's performing how it's performing, or are you somehow incorporating this during the training loop?
Oh, it's not included in it. Like, yeah, and we want to see how good the attention is. I think that's a good question. So basically the adaptive one method to visualize the other method is more reasonable, but like we should the other words and analysis. And if we include that in training, I'm not sure about this. I mean, this is a close. So, like whether the patient model was equivalent to the right and then become justified and so it's a good thing to think about. Thank you.
Yeah.
Hi, wonderful talk. I guess I wanted to hear your thoughts on these NERF-like implicit geometric representations and their role in the scientist and user.
The downside for this for how weird, like the tissue is going to default, the robot is interacting with it. Then is it nerve a good thing to deal with this kind of situation? Like you need to keep retraining it. So it's a bit tricky. But on the other side, I used to do some like a more traditional styles in reconstruction, tracking. But when you get a new image, you need to do a picture matching, do some registration and merge them. It also takes some time. And the accuracy is also you can make cannot guarantee because there's like the error can accumulate over time. So sounds like they still take some time. Then if we can make the retraining of nerve real time enough, maybe that can be. And I mean, maybe that can provide better perception on the deformation thing, but I'm still exploring both directions and I don't have a clear answer like on which one is better. Maybe combine. Yeah.
Very well. Y'all like to do some coffee right now. So I recommend that first of all, we email to either out of big hand. Right, it's gonna be multiple times, full feedback here.
Hi, we have some protein bars and snacks for people if they want to grab something with the coffee. So I'm just gonna put it out there right now. Feel free to grab it.
You want me to do the?
Yeah, I went and asked, they don't have it. So I went and asked everyone at ICRA. They said, they don't have it, they don't know what it is. I asked one that, hey, can we just, like, we need to start. Yeah, I said, we have one of them. I mean, we get it signed later. Yeah, that's it. Not tough.
I've been talking to Jordan Berg.
Yeah.
Okay, cool. Well, that's a lot. Do we have other outlets? Get a chance. Oh, okay. In the floor? Yeah. Just like in the floor.
How about we give them a number? No, I actually, I was in building. Engineering, what's the word? No, the one which Dr. Means Lago, the micro. It's the Clementi station, I would take a bus and go. This is way back, I think it's 2017.
Oh, okay. I even thought it's way back when you were still in first school.
I'm still a PhD. Yeah, so I think this is 2019 hours.
So you were not different, you get off, but like six.
Because I used to still talk to people. So my undergrad advisor was like a student. So through him, so Karthik wanted to. Yeah, so Karthik, yeah, so I worked with them, and through them I went with Dr. So I used to stay like in Tampa. Oh wow, yeah, because I have a family, and I didn't have to. Have you been to Singapore?
No.
How come your family is in Singapore?
No, but they used to work in Singapore. And then luckily I also had a job which was in Singapore. So after undergrad in 2019, I worked. I actually got into undergrad, but the fees was too high.
But where did you do your undergrad?
And then I did my master's with Darwin at UConn. I'm very glad that they were back to class.
More than twice. Actually, I've done a few times. More than twice.
Actually, I saw the black, my course of
So you were in around what?
2017. Yeah, 2017. I was,
You were still an undergrad.
and I used to work with ICRA, so that's why I doubted me. After 2017, the standard you would upgrade to and I wanted to work on central because I figured that we could never replicate this paper because the parameters are already different. But when I came to they were not doing it. I think they were yeah, now you can take any of the assignment of
You know, we have a list. So you're applying some chances for another very burning issues. Actually, now is make sure when you transition, very low.
I mean, after we were like again, I for the later so
Let's take a picture of that.
I mean, there's
All right.
I'm not very good at it. Yeah.
All right. Let me know and we can set.
I'll just take your.
Yeah, let's connect with you.
Okay. Yeah.
Because I'm everything is scanned.
Yeah. Oh, I see. But you want that? Yes. WhatsApp.
Yeah, thanks for coming from Singapore. I was copying the email. Yeah. Wait, so what is the schedule? There is me. No, it's the. I think it's been what. Are you finishing? Yeah. Are you interested in class? To be honest, if I can, yes. If you can or cannot? If I, because my family is close to Singapore as well. My girlfriend is, my family is in Wuhan. So we are where? Wuhan. Oh, Wuhan, oh, the capital of China. So we are trying to see if we can find a middle place, which is, I need to convince her. You know, we have a police working with medical also. Yeah. I think it's good because your expertise is not only for medical, right? Any close loop manipulation. Sensing, manipulation, cutting, I mean, manipulation. I work mostly with multimodal sensors. Yeah. So be it laser or and my interest is in robotics. Yeah, really. Mobile manipulation. Yes. How from the understanding the environment, how do you plan the motion? Yeah. And the motion is not only motion, it's also force and motion interactions. Yeah. I mean, especially for soft tissue cutting, which is the interesting for laser because you don't have contact. So I think what we have to do in a non-contact fashion, how do you like add sensing rules, and all of this to concept? Because anytime you do simulation or anything, you need to figure that out. So that's right. But I think I have been focusing mostly on I work with my core pilot both on even general. This is interesting too because it's not only the cut, it's also the power of the laser, right? And also I don't know, I don't know how many parameters there are. I mean Vivo and I are working. So Vivo is Dr. How's student. Oh, okay. So, hi, I'm Marcelo. That's only so, can you take a picture for us again? A full body one. Selfie is not so good. And I'll send to our common friend. You know, Portland was my student. Oh, really? Long time ago. I think one more. Okay, thank you, Weber. This is like okay. So I was post Dr. Lee's student. He was your student. When he was doing his undergraduate, okay. Then he went to Purdue, and then he went back. So then he became our head recently. Yeah, yeah. Because like the boy I also working with drones. Because what we noticed was that some of the sensors and algorithms we developed for laser-based surgery were like you could just use similar algorithms and put it on the drone. So we've been trying to do something with autonomous drone following. Based on only sensing or acoustic multimodal or camera or acoustic. Now I don't know because some of the problems is depending on the multi-drone system. You need to align people. So what you're going to do is you're trying to get acoustics. But the problem with acoustic in order to very noisy because you have two drones which are similar to drone. So we have been trying to spend different kinds of so the array. Right. So and I've been designing those things. So the surgical robotics part but we have but I have my just the medical robotics more sure no. Yes. Oh yeah, please. Hello. Yeah, I'm here. Yeah. Oh, familiar. Professor Linha. Oh, this now is Yale, right? Linha is Yale University now. Notre Dame. Notre Dame. I applied to NS a few years ago and recommended my application to Robotics. Oh, yes, to grad. Yeah. So did you work with grad now? Now I'm a postdoc in the University of Toronto. Okay. With Ravi? Hi, so where did you do your PhD? Notre Dame, Oh, okay. I've been sitting for a long time. So what is your PhD topic? Is it on systems? Yeah. So I mean, the core is control here. System control. Software robotics. Software robotics. Very good. Last guy is working on software robotics. Yeah, and that's why I really wanted to work in this. Yeah, but then Yeah. Oh no, he doesn't like me. I don't know. Because during my interview, I think Professor I got one right. Did I get one also? I didn't have any purpose. Yeah, same. Your opinion, why he doesn't? When did he interview you? Recently? Right now, after you finish your PhD. Before I finished. Yeah, so at that time I didn't. He was not dean then. He was vice dean of research. He's acting dean. Yeah. Now he's our permanent dean. Oh, I don't have. Don't worry. But please consider us when we're trying to recruit people. So you finished in 2022? No, I finished last year. Okay. You know, Professor Jessica. Yeah, I will be going with them. Yes, yeah. They do very good work in continuum robots. What? Continuum robots. Oh, okay. Oh, Greg is also continuum. Yes, yeah. Jessica? No. Consider. Never mind, don't worry. Oh yes, and also I want to put it we sent this guy in chat, then we connected them with Can you take a photo for us? Thank you. Okay, sounds good.
I mean, otherwise, the microphone here is.
Yes, and then share screen.
Yeah, make sure you share the
Right screen. I shared that. Can you check your screen?
Hi, everybody. We're gonna get started in a few seconds. If we could have everybody start to take their seats, we'll be starting in a few seconds.
What is?
All right, everybody, we're going to get started now for the next track. I'm Michael Yip. I'm going to be presenting the speakers for this upcoming track on autonomous robotics in the era of generative AI. I'm really happy to introduce our first speaker, Animesh Garg from Georgia Tech.
Thank you, Michael. Thank you, everyone, for organizing this. I'll let people settle in. For those of you who do not know me, I'm Animesh Garg. I've been at Georgia Tech. Before that, I was at University of Toronto. And what I'm going to talk about today is my group coming back to surgical robotics after a few years when things weren't really ready for doing autonomy in surgical robotics. And what I'm going to talk about is ideas that I believe are necessary to do for surgical robotics, and then things that we've been doing, not just in the context of surgical robotics, but will very soon be ported over because these ideas have now started working. So for context, I think this is an image from, I think, an op-ed at this point, 8 years ago, when we were trying to quantify levels of autonomy in autonomous driving. Something similar was done for surgical robotics. And the mic is not closeness. Full disclosure. Yeah. I think it's just the height. Yeah, just keep it. Yeah. Okay. Or I can try to be very loud. So over the years, we have tried to quantify what sort of autonomy would look like in surgical robotics. And trying to map it to autonomous driving like this was a very good exercise, but not necessarily what I would call fruitful. Fruitful because in the same way, autonomous driving and what we are seeing in manipulation these days, I would argue surgical robotics has been roughly 3 to 5 years out of phase. Mostly because the tooling and then the complexity of the problem is slightly more challenging than what we have seen in other demos, whether in broader robotics, foundation models, or even just tooling for it, like simulation. So over the years, I have been working on some problems for surgical robotics. These are videos, I would argue, even 10 years to date, actually. The first one was a surgical robotic cutting video we did at ICRA 2015. There was a medical robotics workshop. And the interesting thing was, if you really look at them closely, and I argue that if I hit the date, it would be hard for you to tell that this is from 10 years ago. And that, I think, should not be very exciting. Right? The fact that the 10-year-old video would pass as something as recent. And I think this is the point I'm trying to make. The community in surgical robotics, particularly the community which has been studying autonomy in surgical robotics, has been working with tools and algorithms and methods that have not scaled primarily because of lack of tooling, right? All of these things, I'm going to dunk only on my work rather than anyone else. All of these things were one-offs, right? We built an algorithm, we built a perception system that works for this thing, right? In the first one, we built a system that is literally a detection algorithm for particular patterns. In the second one, we are basically coloring the needle yellow because segmentation back in 2016 did not work, right? And so on and so forth. So I think that this is something that I hope I can convince you Now, this is a slide from last year, meaning stuff that we have seen in the community happening last year. It has been fairly exciting, I would argue, that people have made a lot of progress. One thing, though, by the way, we need an upgrade to DVRK. So if someone is listening, please, we need an upgrade to the hardware that we have. But I think one thing that you can note is we have gone from very simple subtasks, but to more realistic looking subtasks. Note that we are still at subtask autonomy. We do not have the ability to either reason or automate procedures that might be longer than a few seconds, maybe tens of seconds at best. The things that have changed are, in the last 10 years, neural networks have become more capacity, or they can have more capacity, so they can ingest more data. So our behavior cloning algorithms are slightly more robust. Perception systems have definitely become much better. And that is why we see these kind of interesting results. But still, I think a lot of the community has focused on limited training data and focused on solving one task at a time. And I think this is the thing that we have been pushing for, that perhaps we need to at least change our perspective. And I know this is very hard because sometimes data doesn't exist. There are challenges of just putting it out on the robot. But this is a recipe that has yielded a lot of benefit to sister areas. It's worthy a shot from all of us. So this is what we've been doing for the last few years. The first thing we have been talking about is how can we automate certain procedures, right? So this is something that I just showed you, that there are these processes that we can look at, but all of them were done on the real world. And then as a community, we have tried building simulators, but these simulators were, again, either special purpose, did not have good rendering, or were too slow. So speed mattered. Broadly, during my time when I was not working on surgical robotics, we worked on building general purpose simulators for broad set of mobile manipulation and binaural manipulation. And that line of work was called Orbit. Basically, the idea was that you can effectively build a simulator such that the user of the simulator is not going to tinker around physics parameters or collision bodies or stuff like that. It's batteries included, works out of the box. We were very fortunate that the system that we built caught fancy of some people at NVIDIA, particularly Jensen. So they made ISEC Lab. So Orbit is now ISEC Lab. Orbit was renamed and rechristened as ISEC Lab. And now, of course, it has a very large engineering team behind it and a bunch of exciting features. And it is used across industries for data generation, reinforcement learning, behavior cloning, all sorts of stuff. Now, because this system was built for generality, there's nothing to say that we can't extend it to surgical robotics, and that is exactly what we did. We took the idea, the framework that Orbit or ISEC Lab provided, and we extended it to surgical robotics. In particular, we started with DVRK, but there are a number of other robots also included in that framework, right? And the core idea, according to me, was it needed to be super fast, because if the simulator is not fast enough or slower than real time, even though you might be able to simulate it, any sort of learning might not be fast enough. The data collection might not be fast enough. So we showed that the system, because it is using GPU-based physics, was easily of the order of 10 to 100 times faster than most contemporary solvers. And of course, we were able to show simple tasks like proof of concept, like you can do reinforcement learning at scale. These are tasks that are not particularly complicated, but to show that, hey, we can actually do this at scale. You can do behavior cloning, so you can do data collection, you can do policy transfer to real world with the same sort of image-based policies. And this is, by the way, not even to like latest work. This is from last year. This was published at ICRA last year. And we showed that you can use this and integrate this into your workflows. So the Sim2Real can directly be integrated to the DVRK, MTMNP itself. So you can actually collect data from the DVRK interface. And then we created a simple benchmark. So we created small benchmark sets these are not necessarily complex, but more representative of the kind of tasks we have looked at. These are the kinds of tasks that were shown in OSATs back in the day. Notice that turning the rendering up is actually very easy. Turning the simulation fidelity or the physics fidelity has been the challenge. Again, NVIDIA has been very generous. So we built this system. My student, Masood, I don't know if he's here in the room, built this. He went on to an internship at NVIDIA, and now ISEC Lab or Orbit Surgical is now called ISEC for Healthcare. NVIDIA is putting their engineering heft behind the system, and now they've extended Orbit Surgical to include ultrasound simulation, and also, of course, to provide long-term support for the software, which is very useful because a PhD student may not be able to support open source software long-term. But the good news for the community is now we have stable software that is supported by a larger engineering community, adopted by industrial partners, that we can work with. It is easily extensible, so it's not necessary that what ships out of the box is what you want to use. And most importantly, it's BSD licensed. So if you want to use it for whatever you want to do, feel free to do that. So it's not required for you to do that. And this is something that I've been actually very excited about. Now that we have these tools that are easy to extend, so if you're working on a particular type of sensing, or a particular type of robot, or a different type of mechanism, all of that should be brought in. So it's not just that you have to work with DVRK. Of course, the idea is certain things will work out of the box. Now, what did we do with this framework? We worked on this idea that now that we have a simulator, we need to create content. In surgical robotics, we need good anatomy. We need good tissue body models. We need good robots. And we need to show that we can do interesting tasks in these kind of setups. So you can create large-scale demonstrations with visual data, and then actually the simulator will be useful. There's a paper that Masood will be presenting tomorrow in the evening session in surgical robotics planning. The first thing we did was we actually went in and tried to study how can we create good-looking, realistic assets. So this is all simulation, and I think this is not even rendering as well on this as it renders on my MacBook. So this is hyper-realistic simulator. Notice in this case, we are not simulating fluid, so this is texture. But now I think since then it has been extended, so you can actually simulate fluid and stuff as well. Tissue cutting and tissue puncture is something that we are currently looking at to extend this into. But the main idea was that you can take current pipelines, which are basically imaging, whether you do CT or MRI, and then you do effectively reconstruction. This reconstruction can be converted into 3D bodies. These 3D bodies are segmented first. And then we used learning-based methods or GAN-based or sort of generative methods to create realistic looking textures for each organ independently. And then you put it together effectively into a single file. Notice that this is completely procedural, which means that you can make the liver larger by 2x for any single patient, right? Because that is the kind of things we want to do. This is the kind of tooling we want, right? Put the liver larger or make the liver sort of dark brown or create a lesion in the system. These are the kinds of things you can do because those are the kinds of technical problems in perception and control we would like to study as a community, right? Then, of course, we showed that the interface for teleoperation should not be limited to direct DVRK because one, not everyone has a DVRK, and two, they are, well, few. So we have been working to reduce the teleoperation requirements to easily available devices. So this is just using a Quest headset. So you can use any commercial VR headset. And actually, this has been as of 2 weeks ago, extended to mobile phones. So all you need is to download an app to control the robot. Notice, the point is not that this kind of data is surgically this is not what you deploy in the surgery, but this makes the development go much, much faster. Right? Then we have basically created a very simple, what I would call interface to show that, hey, if you collect some demonstrations like this, you can actually do control with behavior cloning. Behavior cloning models have gone far enough. So we created a bunch of these sort of simple tasks. Notice that this time around, we added textures to all sorts of benchmark tasks that earlier were textureless, not as good looking. And you can make it arbitrarily good to a point where I can argue they can make it Turing complete. You will not be able to tell the difference between sim and real. And we showed that as a proof of concept, even simple algorithms, so we are not trying to do algorithmic novelty here, but to show proof of concept that if behavior cloning is the solution, this framework is ready for that. We did some extra work to enforce that in surgical robotics. So what people do in manipulation these days is they would have a camera in the head, which would be some sort of egocentric camera, and they would add wrist cameras. I feel wrist cameras is kind of like unreasonable and unrealistic, and it probably is kind of cheating. It is something that worked for large-scale manipulation. But if you take the same algorithm and apply it to surgical robotics with only 2 cameras, it doesn't actually work. So the paper by, I think the Johns Hopkins people actually added cameras to the wrist, just to showcase that this works. So this is something that we were really sort of adamant about, like we should not be adding cameras to laparoscopic tools. Just does not make sense. So we worked on this, and we basically showed that one, the system can be trained purely in 3D space, so then it will be viewpoint robust, and you do not need wrist cameras. And I think this was just to show that if you do this correctly with reasonably large data, you can get generalization otherwise as well. But the main point was, if you use 3D, which is something that is easy to simulate and fast to simulate, then you can actually keep the simulator setup or the DVR sort of your experimental setup roughly the same without need for changing any hardware. Now I want to talk about some of the work that we've been doing outside of this domain, but has yielded, according to me, surprisingly interesting results. I want to say, like, these results have surprised me. The students have surprised me. So we were working on this problem in my lab, where the idea was we wanted to do lab automation. And the idea was, can you put any of these vials in the socket, right? And you could imagine that this kind of problem could be applied to a surgical room, but not on the table. But the main point turned out was, despite the fact that the VLMs or VLAs would promise that this problem would be fairly easy and work out the box, turns out that currently no solution works. So you take your favorite solution, and either it will have to be task specific, the same problem we saw earlier, or a VLM would not work, basically. So what we do is we say if you take a VLM and you basically say, can you place it there? It can tell you, yeah, like somewhere there, right? But if you have to put a peg in a hole, there is a problem of pose estimation. You need to be exact. And if the, let's say, margin is 5 mm or less, then definitely a VLM is not going to do. VLMs are mostly 2D to begin with. Even the 3D versions are not very good. So we said we can actually combine this sort of hybrid system where the language and the reasoning can be solved by VLM. So think of it like this, that if you say, put the vial in the vial rack, you're by design ambiguous. So then the system can tell you, okay, these are all the possible locations you could place it in. You pick one of them, and then you decide that now this is a point cloud matching pair. For this problem, we can train data, train in simulation. So now the problem has been reduced to, you're given 2 point clouds, let's say a pen and a pen cap. How would they fit together, right? And you can, interestingly, train this purely, no surprise, because I'm a simulation chauvinist, purely in simulation. So you take simulated images, simulated 3D point clouds, and a large set of objects. And once you do that, this was the surprising result. We were able to do this for fairly complicated tasks. This was not necessarily in the training data set. And you can keep doing it for all sorts of things, right? None of this was training data set. And the fact that we can train effectively a very general purpose model, pick and place, a single student on a single desktop, purely in simulation, should give us all hope. We are not yet edged out by the industry with 1,000 GPUs. So there's a lot of interesting things you can do in this research, and I believe this is the kind of work we need to bring to surgical robotics. think my time will run out. So before that, I think this is interesting. Over the years, in addition to low-level skills, we have also been very interested in building what I would call high-level reasoning systems. And the idea has been that can you interact with these systems to effectively provide a high-level reasoning or a plan? So at IROS last year, Masood worked on this idea that can we do language-guided control? So in this case, you basically would interact or talk to the system to provide it some high-level goal, and then this high-level planning would effectively create an agentic system, if you will, right? So a perception system tells you where to go, and then you actually do the task. And this basically can be applied to a variety of different subtasks, the kind that I showed you for surgical robotics. And you can basically interact by providing as much level of detail as you may want. And then this basically allows you to create longer horizon tasks that would not be possible easily with, let's say, reinforcement learning, because the horizon is way too long, or even behavior cloning data would be very overfit. So you're basically providing skill level instructions directly in language through an interactive interface. Of course, this was a proof of demo last year. At this point, this can be done hopefully much, let's say, faster. Since then, there's one thing that we have done was the idea that you are effectively doing planning with language models is a very powerful idea. This is something that the community has been working, including us, that, hey, can we use language models as planners directly? And effectively, when I use the word planners, they are explicitly outputting plans as programs. Why? Programs are verifiable. This is very important to us as a community. However, this direct output model has been limited in scope, because if you directly output a plan from an LLM, you're basically saying the LLM should be a neural Turing machine. Effectively, it can solve an arbitrary search problem. Instead of doing that, what we found was a slightly more interesting framework, where we say that instead of having a neural Turing machine, let's do something more interesting. We should give us an English description of the task, or a natural language description of the task. And instead of outputting the plan, it should output the domain description. Why? Because if it can output the domain description and all of the predicates, then I can use a specialized planner. We have many of them. We can use verifiers for these kind of things. The problem is domain description is a very manually laborious process. So this is what it looks like. You provide inputs. Oops. I don't know. Yes. You provide inputs. These inputs would then be effectively converted into a language-guided PDDL. Now, PDDL in one shot may not be complete, right? So you may say, open the door, but the system doesn't actually know what an open door means. So what you do is you actually do predicate grounding. This is also done purely automatically without human in the loop. Now, with this system, you can actually do planning. Once you do planning, the plan may or may not work. If it doesn't work, you can use this feedback to improve the domain description. This is very important, because now what I've just told you is a system that is effectively building what I would call a world model, right? And this world model improves iteratively the more interactions you see. So this allows you to do simple things. So for example, if the input data was build sort of basic stacks of 2 or 3, you can now start doing arrangements that are more complicated. Why? Because the only thing that is differentiated between these tasks are the predicates, right? When you check, is this a pyramid? And this is something that VLMs are very good at. So you can actually do very interesting continual learning tasks, starting from very simple examples. And this is by design supposed to be simple, just to show that, hey, we can solve very simple planning problems and then create verifiable solutions for more complicated settings, purely with an automated sort of agentic system with LLMs in the loop. With this, I think I would like to bring this to a close. The main takeaway, hopefully, from today's talk or this short lecture should be surgical autonomy has a lot of promise and a lot of tooling that was not there 10 years ago, particularly in perception, planning, and control. is now evolving to a point where we can actually, as a community, come together. In terms of planning, we definitely have very good LLMs and VLMs, and they can do a lot of complex tasks. As a community, we have a lot of data, surprisingly much more than most other communities. On the control side, the fact that behavior cloning models with some amount of or modest amounts of data work, we can also use our real data and augment it with simulated data. And as a community, if we work on better simulators, we can make progress in a manner that would be reproducible, benchmarkable, and perhaps not a demo video only. With that, thank you very much, and thank you for inviting me and for the privilege of your attention.
All right, questions for Animesh?
Yes. Lot of work both within surgical autonomy and broadly, where these days perception models are trained purely with synthetic data. That's one. Now, Interestingly, at least the DVRK style systems or tendon-driven systems are primarily driven in what you would call a position-based dynamics. You're not using forces or you're not doing inverse dynamics for control. For position-based systems, the symmetrical gap is much lower because you can actually just set the position of the robot. Now, the only thing that remains is the actual anatomy or the system. That, I think, is a gap that I do agree. So for soft object simulation and fluid, somewhat, cutting, for example, which is a very important piece, or basically tissue fracture and tissue tearing, that in principle has been shown to work, but hasn't been scaled and made available broadly enough. So there is a gap, but I do believe that instead of trying to shun away from this, we can just improve the simulator because that is a much more scalable solution. Yeah.
All right, let's give our speaker another round of applause. I'll do that in this. All right, and our next speaker is Jiying Wu from Vanderbilt University.
Thanks for inviting me here to present at this workshop. I apologize if you've been to ISMR last week and saw this. It is a little bit repetitive, but that's okay. I do love the discussion leading up to this though, because it sets up my talk nicely of I want us to be learning from real data. I want to create the 3D representations of scenes so that we don't have to worry about the sim to real gap because we're already going to be in real. And to set this up, I'm going to talk specifically about central airway obstruction. It is when tumor grows into people's airways, generally from lung cancer, but possibly from other causes. And the goal of the surgery is to go down a patient's throat, essentially, and remove that tumor. The treatment is often very difficult. Not all centers provide it. So we think that automation can increase both availability and quality of the surgery. But also important for us, it's a good proof of concept because your trachea is a very tubular structure. It is rigid, it is in air, and therefore it has fairly good visibility conditions for demonstrating automation is possible through vision-based guidance. So first, our test bed, we took some sheep trachea, I guess, or pig trachea, and put chicken breast in it. So all of the videos I show will be on this model going forward, where we super glued chicken breast to trachea. But really, to me, what we need to do to guide automation is we need to learn sort of two orthogonal sources of information. One is the geometric reconstruction of the scene. So how do we get the point cloud of what we're actually looking at, right? So some parts of this problem is solved in Da Vinci system through stereo reconstruction. That's an incomplete reconstruction, but it sort of works, but not for this case where it's a really tight space. We don't have space to put another camera. So we're going to look at monocular reconstruction. And then the other side is semantic information extraction. So, okay, given this view, what are we actually looking at? What's the tumor and what's the trachea? And once you have both of these sources of information, you can combine both of them to a segmented point cloud, which according to our collaborators on automation side is what they want to practice or to train their robots on for either learning from demonstration tasks or for actual model-based planning tasks. So how do we get there? Well, let's look at the semantic information extraction first. So this is work done with collaborators at Vanderbilt University, where we're taking a super straightforward approach for the initial step. We train a UNet, everyone's favorite neural network in segmentation, it feels like, with deep supervision. We train it with DICE and binary cross entropy loss. And then we do four-fold cross-validation to see what the best hyperparameters are. And I'm going to present some results on this. You'll see that it works well. One caveat I want to point out going forward for segmentation is that we do eventually demonstrate it on eutrachea, but all the numerical results were evaluated with trained test splits on the frame level, not on the trachea level. So we did see a little bit of performance degrade when we moved to a new trachea, but it mostly works. It works well enough to guide automation, let's say, which really is the goal here, right? And so you'll see that in the different sort of scenarios, the segmentation is reasonably stable. In the sort of first stage, the exploration, that's sort of our nicest videos. But then on the right side, you'll see there's fogging possible, light changes, and the basically, we annotated enough data until we could cover all of those scenarios based on our trachea model. What was interesting to me was that people could do this, but people aren't that great at segmenting where the tumor is either. And so that's one of the reasons we move forward with this, despite not testing on new tracheas, or why we think it generalizes in new trachea, is because guiding actual surgical removal doesn't seem to require 100% dice score. If we ask two raters to say where is the tumor, and the raters don't actually agree for a lot of time. They only achieve about 90% overlap in where they say the tumor is. You'll see that the bottom right graph shows that it drops a lot for the smaller tumors in particular. And so if we're far away, then really we don't care how well we see the tumor, because our automation strategy should be to get closer to the tumor before we start resecting it. And so we're really looking at the simpler cases where we're right up against the tumor. So, it seems to work fine. And we see that our network dice score has higher dice than between the raters. So we decided we have extracted our semantic information. Let's look at the geometric reconstruction. And so for geometric reconstruction, our first sort of method to approach getting the point cloud data is to use structure from motion, particular neural network-based structure from motion, because the neural networks tend to find better features in the anatomy endoscope images compared to, say,